So far, most of the series that we've worked with in the last two sections have had all positive terms. In this section and the next one, we're going to look at series that have positive and negative terms. And to work with these, we're going to use the alternating series test, which says if a sub n is greater than 0, the alternating series, and there's two of them, -1 to the n times a sub n, and -1 to the n plus 1 times a sub n. Both of these series converge when two conditions are met. And the first condition is that the limit as n goes to infinity of a sub n is 0, and that a sub n plus 1 is less than or equal to a sub n for all n. So this is our alternating series test. Let's look at some examples. Our first example is this one. -1 to the n plus 1 times 1 over n. And for this one, we could say that the limit as n goes to infinity of a sub n is equal to the limit as n goes to infinity of 1 over n, which is 0. So the first condition is met. Now let's look at the successive terms. A sub n plus 1 is equal to 1 over n plus 1. And a sub n, of course, is equal to 1 over n. And this term, a sub n plus 1, is always less than or equal to a sub n. So we've met our other condition. And we know that this series converges. Here's another alternating series that we'll check the convergence for. Okay. In this series, note that when n is greater than or equal to 1, that ratio n over n plus 1 is greater than 1/2. So now I have 2 to the n minus 1 over 2 to the n is going to be less than n over n plus 1. I'm going to cross multiply now and see that 2 to the n minus 1 times n plus 1 is equal to 2 to the n times n. This lets me say that n plus 1 over 2 to the n is less than or equal to n over 2 to the n minus 1. So now I can say a sub n plus 1 is equal to n plus 1 over 2 to the n, and that is less than n over 2 to the n minus 1, which is the a sub n. So we see that a sub n plus 1 is smaller than a sub n. And now we will apply Hopital's rule and say the limit as x goes to infinity of x over 2 to the x minus 1 is equal to the limit as x goes to infinity of the derivative, so we get 1 over 2 to the x minus 1 times the natural log of 2, which equals 0. Therefore, this limit and this limit, the limit of n over 2 to the n minus 1 as n goes to infinity is 0. Okay, so by the alternating series test, this series converges. We have to always remember when we're using the alternating series test that we have to meet the conditions to use it. So let's look at this series. Which is -1 to the n plus 1 times n plus 1 over n, which gives us 2 over 1 minus 3 over 2 plus 4 over 3 minus 5 over 4 plus 6 over 5, and so on. Okay, this passes the second condition of the test because a to the n plus 1 is always less than or equal to a to the a sub n. Okay, but we can't use the alternating series test because we didn't pass the first condition that the limit equals 0. So we can't use the alternating series test in this case. Now if I have this series, okay, and you can see here 2 over 1 and 1 over 1, 2 over 2, 1 over 2. So the denominator repeats once and the numerator is just 2, 1, 2, 1, 2, 1, 2, 1. Okay, now this meets the first condition because as n goes to infinity, this goes to 0. Okay, but I don't meet my second condition, which is that every term is less than the one before it. Okay, clearly 2/3 is greater than 1/2, 2/4 is greater than 1/3, and so on. So here we also can't use alternating series test. Okay, so always check your conditions before you jump into applying a test. If I have a converging alternating series, sometimes I can use the partial sum S sub n to make a reasonable estimate of the actual sum. The error involved in using S approximately equal to S sub n is called the remainder, R. And R is equal to the actual value S minus S sub n. This is the remainder. Okay, we have a theorem, 9.15, and this is on page 625, called the alternating series remainder. If a converging alternating series satisfies, if we have a sub n plus 1 is less than or equal to a sub n, then the absolute value of the remainder r sub n involved in the approximation of s using s sub n is less than or equal to the first neglected term. So if I wanted to write that in symbols, it would look like this. Absolute value of s minus s sub n is equal to the absolute value of r sub n, which is less than or equal to a sub n plus 1. Okay, and there is a proof of this theorem in Appendix A of your textbook. Let's use this theorem to approximate the value of an alternating series. So I've got a sum from n equals 1 to infinity. of negative 1 to the n plus 1 times 1 over n factorial. So the first few terms are 1 over 1 factorial minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial, and so on. Okay, we know that this series converges by the alternating series test because I've got 1 over n plus 1 factorial, which is always less than or equal to 1 over n factorial. And the limit as n goes to infinity of 1 over n factorial is 0. So the sum of the first 6 terms, 1 over 1 factorial is just 1 over 1. 1 over 2 factorial, 1 over 2. 1 over 3 factorial, 1 over 6. 1 over 4 factorial, and this is minus, not plus, is 1 over 24. The next term would be 1 over 120, and then 1 over 720. When I add those all up, I get 91 over 144, and that's approximately equal to 0.63194. If we want to find the remainder for this calculation, we have absolute value of s minus s sub 6 is equal to absolute value of r sub 6, which is less than or equal to a sub 7, which is 1 over 5040, and the decimal for that is 0.0002. So the sum S is in between this 0.63194 minus 0.0002, so 0.63174. And then I have to take this number and add the 0.0002, which is 0.63214. Okay, so now I have an estimate for the sum, and I've got it narrowed down to a pretty small range of how accurate that sum is. We can also use these calculations to figure out how many terms we need, how many partial sums we need to get an estimate that's within a certain range. Let's look at that. Okay, we have this summation, n equals 1 to infinity, negative 1 to the n plus 1 over n to the 4th. And we want to estimate the sum of the series here be less than or equal to 0.001. Okay. We know that the remainder has got to be less than or equal to a to the n plus 1, which is equal to 1 over n plus 1 to the 4th. So to get this error, we must satisfy that 1 over 1 plus n to the 4th must be less than or equal to 0.001, which tells us that which tells us that 1 plus n to the 4th must be greater than 1,000. And so n must be greater than the 4th root of 1,000 minus 1, which is approximately 4.6. So I need to round this up. I can't have 4.6 terms, so I need to have at least 5 terms to get the accuracy that I want. Okay, and if I go back and use 5 terms here, I get that my S is approximately equal to S sub 5, which is approximately 0.94754. Okay, and this has an error of less than 0.001. Okay, to wrap up this section, we're going to talk about absolute and conditional convergence. And we have a theorem on page 626 called the absolute conversion theorem, which says if the sum from n equals 1 to infinity of the absolute value of a sub n converges then the same sum without the absolute value also converges. Okay, and make sure that you get those 2 parts of this theorem in the correct order, because the converse is not true. We cannot say that just because a sub n converges the sum, that the sum of the absolute value of a sub n will also converge. It only works this way. Okay, to define absolute and conditional convergence, this is absolutely convergent if this converges. And we would say that this sum is conditionally convergent when the sum of a sub n converges but the sum of the absolute value of a sub n diverges. Okay, so that's the difference between absolutely convergent and conditionally convergent. Now we're going to use these definitions to determine if series are absolutely convergent or conditionally convergent. So we'll start with this one. Okay, we'll just write out the first few terms here. Got 0 factorial over 2 to the 0 minus 1 factorial over 2 to the first plus 2 factorial over 2 squared minus 3 factorial over 2 cubed. Okay, this is an alternating series, but the alternating series test does not apply because the terms are not going to 0. Okay, but we can use the nth term test for divergence, and we can conclude that this series diverges. Okay, let's look at the other series. And the first few terms here would be negative 1 over square root of 1 plus 1 over square root of 2 minus 1 over square root of 3 plus 1 over square root of 4 and so on. Okay, we can show that this is convergent by the alternating series test. And because this p-series this equals 1 over square root of 1 plus 1 over square root of 2 plus 1 over square root of 3 plus 1 over square root of 4. Since this p-series diverges, even though this converged, we have to say that it is conditionally convergent. Because we had one converge and one diverge. In our last example, we're going to look at two more series and determine whether they are convergent, conditionally convergent, or divergent. And this one is -1 to the n times n plus 1 over 2 over 3 to the n power gives me -1/3 minus 1/9 plus 1 over 27 plus 1 over 81. We cannot use alternating series on this test because I've got two negative terms and then two positive terms, and then two negative and two positive. So I can't use alternating series test on this. However, we could make this equal to something a little simpler. If I took the absolute value of this, I could make it look like this. This would always be 1, and I'd have 3 to the n. And this is a convergent geometric series. And my r is equal to 1/3. Okay, so we could say that this is absolutely convergent. Okay, so if it's absolutely convergent, then this is also convergent. Okay, let's look at another one. Okay, and the first few terms here are going to be -1 over natural log of 2 plus 1 over natural log of 3 minus 1 over natural log of 4 plus 1 over natural log of 5. Okay, and if we use the alternating series test on this, we find that this converges. However, if I take the absolute value of this series, I get 1 over natural log 2 plus 1 over natural log 3, 1 over natural log 4, 1 over natural log 5, and so on. And this diverges by direct comparison with the harmonic series. Okay, so this part converges, but this part diverges, so we say that this is conditionally convergent. Okay, you might see in your textbook that there's one more example about rearranging the terms of a series. We're not going to cover that. It's not in your homework. It will not be on a test.